Hi, this is Tom, and welcome to Lesson 34, Linear Regression. So what we're going to do today is we're going to consider a data set, and here's what it looks like. It's 1, 1, 2, 2, and 3, 2. That's our data set, and let's take a look. First thing I want to do is let's make a scatter plot of this. Make a scatter plot. Okay, and notice we have ordered pairs, and so when we make our scatter plot, our x values are on the horizontal axis and our y values on the vertical. So 1, 2, 3, and then 1, 2, and 3. So the point, now I use another color here. How about this pink? So there's the point 1, 1. And then the point 2, 2 is right up here. 2, 2. And the last point is 3, 2. So we're going to do a few things with our data. So first off, we have our scatter plot. And what we're going to do is we're going to decide if this data is correlated. And then if it is, well, if it is, then we're going to understand the title linear regression, and that is we're going to see how a line would fit this data. So here we go. First thing we need to do is, I think that's my green, is let's calculate R. So we're going to come over here, we're going to calculate R, the correlation coefficient. And we did this in the last video for some other data sets, but I always think it's good practice to review. And the formulas look big, but remember we could just break it down to a table. And here's what we did. We put our x value, our y value, the product of x and y, x squared, and y squared. So we just start by making a table. And let's see, our first data value, our first ordered pair is 1, 1. Our second one is 2, 2. And our third one is 3, 2. Okay. So product of x and y is 1. X squared is 1. Y squared is 1. Okay, x times y is 4 for the next pair. X squared is 4, and so is y squared. Now for our next data value, the product is 6. 3 squared is 9, and 2 squared is 4. And now our final row is going to be the sum. So the sum of the x's is 6. The sum of the y's is 5. The sum of the xy's is 11. The sum of the x squareds, that looks like a 14. And the sum of the y squareds appears as 9. Okay. And I think we've got that. So now we have all the pieces that we need. And so let's remember our formula. Our formula for R is n. And remember, n is the number of ordered pairs, which in this case is 3. So it's n times the sum of the xy's minus the sum of the x's times the sum of the y's divided by, we have this big square root. And the square root is n times the sum of the x squareds minus the sum of the x's squared. And that's the first set of parentheses. And the second set is n, the sum of the y squareds minus parenthesis, the sum of the y's squared parenthesis. Bring our square root out. And here we go. Let's calculate this. So n we said is 3. The sum of the xy's, that's the 11, minus the sum of the x's, that's 6, times the sum of the y's, we have is 5. Divide all of that by square root of So we have n is 3. The sum of the x squareds is 14. Oops. Let's write it this way. 14 minus, so now the sum of the x's is 6, and you square it for 36. Parenthesis, parenthesis. Then we repeat this for the y's. It's 3. The sum of the y squareds is 9 minus, well, the sum of the y's is 5. We square it. That's 25. All right. If you simplify this, we have a, looks like a 33 minus a 30, so it looks like we have a 3 in the numerator. And then in the denominator, this is going to be a 42. Looks like we have a square root of 42 minus 36. Well, that's just 6. And then it looks like we have a 27 minus 25. Well, that's going to be 2. And if you put that in your calculator, we actually come up with 0.866. So here's what we're going to do. When you go on in statistics, you'll find out that there's a formal way of deciding if the correlation coefficient is high enough. But for now, in our lessons, what we're going to do is this. We say if the absolute value of r is greater than or equal to 0.8, we're going to say then the data, we're going to say, is significantly correlated. And so if in your practice you come up with problems that ask you to come up with to run a linear regression, but if r, the absolute value of r is smaller than 0.8, like closer to 0, well, then it's not even worth calculating a line, and so you can stop. And that would be your answer. Well, in this case, since we do have a set of highly correlated data, so now what we're going to do is we are going to now find the line of best fit. Okay, now in order to do this, we need three more equations, and let me give these to you. So the actual equation of the line is y prime, and we'll talk about that, equals the letter b times x plus the letter a. Now, the x, that's actually the x value for a data value. Now, notice this. We said that the other value on the ordered pair was y, but this says y prime. And what it is it's really close to y, and this is what we call the predicted value of regression. The predicted y for some x. And we're going to practice that too. So this will make more sense as we work through it. Now, also, if let's do this. A is calculated with this rather large-looking formula, and here it is. It's the sum of the y's times the sum of the x's squared minus the sum of the x's times the sum of the xy's. Now, if you feel intimidated by that, that's normal, but we're going to work through it so you can see that actually we have done all the hard work above when we made our table. And then in the denominator, we're going to have an n times the sum of the x's squared minus the sum of the x's squared. And for b, we have a similar large equation. We have n times the sum of the xy's minus the sum of the x's times the sum of the y's. And this is also This has the same denominator as the a formula. It's n times the sum of the x's squared minus the sum of the x's squared. So we're going to use a and b, and we're going to use y prime, and we are going to find a line of best fit. So we're going to stop there, and next video we'll get this done. See you then. Thanks for watching.